I'd like to start by introducing our group. Myself, Dominique, Toumadje, Anita, Masson, Anoop, Nair, and Victoria Ho. Together, we make up the inexpensive heart rate detector. So our project was to create an accurate, inexpensive, robust heart rate monitor. Heart rate monitors are one of the most frequently used pieces of medical equipment in hospital and primary care settings. Their ability to affect the health and well-being of the general public is quite high. In developing countries, they face a problem with inadequate supplies and common devices such as these. We take a case study in Malawi, which is the 10th poorest country in the world. They have a healthcare system which is vastly under-resourced. They have approximately one doctor for every 50,000 people, so the time between doctor visits can be quite long. A heart rate monitor device like this is very important so that you can monitor your vital signs in order to know whether you need to see a doctor and with what sense of urgency. So there are several methods that you can use to extract information from the body and turn that into a heart rate. The first is based on electrocardiography, which measures the electrical activity of the heart. The second is oximetry, which measures the light difference in soft tissue when the heart pushes blood through an artery. And the third is photocardiography, which records the sounds of the heart. So we began to develop a solution by first choosing among the sensor methods. We decided to choose ECG because not only was it the least expensive sensor method, but it can also provide a unique waveform which you can use for diagnostics. We then performed market research in order to find devices on the market that were similar and be able to find cost and functionality for our design. We came up with the final product, which would cost at a retail price of less than $20. It would have a digital display and would have an audible click in tune to the heartbeat. With that, I'd like to turn it over to Anita, who's going to talk about how we extracted the ECG signal from the body.
Good morning. First of all,
You're making fun of Dr. Sutton.
First, I would like to concentrate on our input, which is the ECG signal. The ECG signal is shows the electrical activity of the heart. Because of its very distant R wave, it's very easy to count the heartbeat, and we just need to measure the time between two consecutive R waves. One of the major characteristics of this signal is its small amplitude. It goes from 1 to 5 millivolt peak to peak. Because of that, it's very susceptible to noise. As much as we amplify it, as much noise we get amplified. This shows the picture. This picture shows the signal coming directly taken from the skin. And as you can see, we cannot use this. We would not recognize any other waves. There is three major noises to take care of. The first one is the baseline wandering. It's caused by very smooth motion, like respiratory motion, breathing, and it makes the R wave drift from the baseline. It occurs before 0.5 Hertz. The second common noise is the electrical signal caused by the muscle contraction, also known as EMG. This noise occurs all across frequencies, but especially above 150 Hertz. The last noise is the electromagnetic interference coming from the plugs and lights, and it's at 60 Hertz. This is our preferred design. I will talk about each stage in the following slides. The first stage is the differential amplifier. As you can see on the output of a great deal of the noise has been already filtered out. It's because our common mode rejection ratio is of 61 dB, which is pretty high. And it's also been amplified by 250. The next stage is our bandpass filter. As you can see in the frequency response, it gets rid of the frequency below 0.5 and above 150. The first stage is our 20-notch filter. It suppresses the noise, the 60 Hz noise. Now you can see our output is ready to be amplified, and that's our last stage, the amplifier, which multiplies our output by 11. This is the comparison of the two frequency spectrum. This is the input before any filtering. As you can see, the 60 Hz noise is very present, and after filtering, it has been very suppressed. The harmonic noise also has been attenuated. Now I will let Anoop show you the digital. Thank you.
All right. Now we get the final output from our analog circuit. This is what it looks like. Now we need to determine a heart rate and display to a 7-segment. In order to do that, we used a microcontroller. We used Atmega 168 as our microcontroller, and also we used a STK 500 element to test and debug our code with the real-time signals. Another important feature of this microcontroller is it comes with this analog to digital converter, which will convert the analog signal to a digitized form. Once we get the signals digitized, we need to calculate the heart rate. In order to do that, we need to have some kind of algorithm. We used multiplication backward difference, or called MODB, which will multiply the difference between two samples. If the difference between 3 consecutive samples are positive, we calculate its product. Once we get the product, we check to see if it is greater than our threshold. If it is greater than our threshold, we store the corresponding time value and the corresponding amplitude. Once we get that, we can easily calculate the R to R difference between those times. Once we get that, we can calculate our BPM using our formula. And once we get the BPM, we calculate the heart rate based on average of last 5 BPMs. Once we get the heart rate, we will display it to a 7-segment, and an audible beep will beep accordingly. Now I will hand over to Victoria. She will take you through this testing process.
During the development of our project, we complied with all the good manufacturing practices for medical devices by establishing and maintaining all procedures as well as documenting all of our tests. So the last thing to do is to see how our system will work with different people.